Recording in progress. So welcome everybody to lecture 6. Today we start materials. So for project 6, we'll use the lighting that you did for project 5. Come on. Wow, Zoom is not happy today. Project 5, lighting becomes project 6, materials. Don't forget, project 6 will eventually become project 7. Make sure that you have multiple copies. Make sure you have backups. Because if you are only working on the same scene through all these different assignments and Maya corrupts your file, which it's been known to do, it's disastrous. So please make sure you take project 5, duplicate that whole Maya project folder or copy it, put it in another location, rename it to project 6, put it back in whatever location you want it to work on, and you've got a backup of it. Today, well, let's see, project 6 for materials, we break it up into 2 parts. Willie said, literally just happened last night for my animation portfolio. Oh, yeah. So it got corrupted, huh? Yep. Always make copies. So we break materials up into 2 parts. Today, we will be doing reflections, specularity, and roughness on materials. And on Wednesday, we will be doing transmission, which is basically how light passes through an object, transparency, and refraction. All right, so let's just go to a more neutral screen. Got something down at the end? No. All right, let's just create a new slide just for fun. There we go. Get rid of that, get rid of that. Okay, so project 5 lighting becomes project 6 materials. Project 6 materials is in 2 parts. Today we are working on reflections, specularity, and roughness. And on Wednesday, we are working on transmission, transparency, refraction, basically glass. Today we are doing what are called reflective materials. And reflective materials come in 2 different types. One is called conductor, which is metal materials, everything metal related. Any others are called dielectric, which are basically sort of insulators, if you want to look at it in electrical terms. It's basically things that are anything other than metal. Even glass comes under the dielectric moniker. All right, so brief overview. So you're going to want to download the Lecture 6 demo files, Arnold zip. We're going to do a little demo after break together, kind of go through basic reflective material properties. We've also provide for you bread reference and thermos reference, thermos being a brushed metal material similar to my water bottle here. which is basically brushed metal. It's metal, and you can see it's got an interesting property. Instead of reflecting lights in a circular pattern, it reflects light in a vertical manner, because the nature of the material itself. All right. So office hours tomorrow on Discord from 10 to 4 p.m. Thursday's the same. We will have a Zoom open lab. Either Frank or Ari will be running it on Thursday from 1 to 5 p.m. Eastern Standard Time, and that's optional for online and campus students. All right, so as I mentioned, reflection, specularity, roughness. We're also going to be dealing with anisotropy, which is basically metal. Well, let's be a little more accurate. Basically brushed metal. This thing called BRDF, which all advanced materials have, including what are called PBR materials, physically based rendering materials that you find normally in a traditional real-time gaming engine like Unreal or Unity. Including, like I said, real-time materials, which are typically called PBR, physically based rendering materials. All right, so basically bidirectional reflectance distribution function is we measure material reflectivity, or actually we measure materials for other things too, besides just reflectivity. So we measure objects, we measure materials in two different directions so we get a more accurate result. Because when we look at things, as humans, we generally notice reflectivity and two distinct viewing angles. One is when we look at a material or an object directly, and the other is what we see on the side of that object. Sometimes reflectivity is a lot more noticeable on the sides of objects rather than when you look at them face on. We've also got a research discussion due Thursday, the same time that Project 6 is due. So on Thursday, we have Project 6. We have the material discussion for Project 6. And we also have the research discussion. All right, now, when we talk about materials, they are not maps. They are not textures. A lot of people say, oh, we're going to talk about materials. And they go, oh, great. Can make all these materials in Substance and export them. No, you're not exporting materials. You're actually exporting maps that go into the material to help it describe how it should look or how the object should look. So that part is really important. Materials tell us in the real world, materials tell us, is something shiny? Is something rough? Does something look metallic? Does something look like concrete, like wood, like fabric, like, you know, paint on a wall, carpet on the floor, brick outside, grass? All those things we get from a material property, not necessarily from the color part of it either. A lot of times we associate color and materials together. Well, I should say pattern and materials. Like wood. When we say wood, probably immediately what comes to mind is all the grain in the wood. Okay, but aside from that grain, that wood has a distinct property. If the wood is outside, still on a tree, it's going to be pretty rough and not very shiny. Okay, you go into Home Depot, Lowe's, any kind of lumber place, go look at wood planks. They're usually pretty rough because they're not finished. They're not sanded smooth. They're not stained. They don't have a coating on them, like urethane or varnish. But we can still identify what they are even without the color. It's the material property that we're interested in today and on Wednesday. Like I said, we're just going to deal with reflectivity today. And then on Wednesday, we'll get to glass. We'll get to transparency. Because you're going to have a lot of each. Well, not a lot. You're going to have a lot more what we call dielectric and conductor materials than you will glass. You'll have some glass, but not as much. Because most objects are not transparent. Yeah, we have, glass, we have drinking glass, we have plastic bottles, but generally everything else is opaque. Right? Does that make sense? Any questions? How about out there in the Zoomosphere?
Good. I'm all good.
Okay, thank you. Gaetano, any questions? All right. So let's clear this and keep going. All right, so research discussion. This is a chance for you to research something you are passionate about. Why you came to Full Sail. What do you love about 3D art? Whether it's animation, whether it's modeling, whether it's game development, game design, game art, rigging, like I said, animation's another one. It could be any aspect, could be rendering, could be shading and lighting, could be materials, could be texturing. It doesn't really matter. It's a chance for you to do some research on what you're passionate about. Now, there are several resources that you can use. I've got some databases here from EBSCO. From what I understand, you guys have used EBSCO before in some previous classes. All right, so pick one of the databases. I usually recommend the complete databases because you're not just limited to a category. Put in your search parameters. Hey, I want an article on animation, or I want an article on game art, or I want an article on rigging. I want an article on visual effects or animation or anything. Right? And see what you get in there. Now, other possibilities are, I've got a couple of online journals that you could use. One is Gamasutra. They've just recently changed their name. So if you type in Gamasutra, it's now called gamedeveloper.com. Think it is the same, it's basically the same place. They're trying to change their name. All right, so this is a fairly respected journal. Let's go back to here. There we go. Or I should say online journal. Another possibility is something called Game Studies. It's an international journal of computer game research. This is pretty scholarly. A lot of people who write the code, who develop the various functions, collisions, visual effects, real-time rendering, real-time materials, animation. It's really, like I said, a little more scholarly than Game of Sutra, which is more towards notifying or keeping people updated on what games came out, what news is in the industry, and also the games. Game of Sutra or game developer is real big on doing what are called postmortems on games, which is basically when a game gets completed, they get all, the people who are developers together and they say, okay, what went right? What went wrong? What would you do again? What would you change? And they go through, kind of take a self-assessment. And those contain great bits of information in there. So you can use either Game of Sutra, which is now game developer, or game studies if you are in gaming. You can also use EBSCO. If you find another online article, I would like to see that before you use it. I want to make sure the source is legitimate. What we're trying to do is eliminate somebody's opinion about something. We want to have a little more than just an opinion. Oh, I hated that, it was stupid. Right? We're trying to find out, okay, this didn't work. Why didn't it work? We would like to have some kind of knowledgeable information rather than just the usual internet stuff that's out there if you're not careful, if you don't filter it. All right, so for this, you will need to create a citation if you choose to use Game Developer, Game of Sutra, or Game Studies, because they do not provide a citation automatically. So you will have to do one. And we use, don't forget, we use the APA citation format. If you're using EBSCO, EBSCO has kind of a home page that will take you, before you go to the article, it'll give you things like a permalink. It'll give you the option for a citation button. It'll give you various citation formats. And then it'll give you a PDF or HTML version of your article. So that's the first thing. Second thing is the link. The link must be underneath the citation. So it's got to be citation first, then link, and then your article. Now, for the article, I do not want a typical, this article said this, blah, 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 basically giving me a recap of it. What I want is, how do you relate to that article on a personal level? Why did you choose it? Why did it motivate you? If it didn't motivate you, why didn't it motivate you? Did you find it useful? Did you find it not useful? How that all relates to you on a personal level. I like the you component in there because that gives the reader, the viewer, more information about you. And it's also a chance for you to share yourself with other people. Does that make sense? So citation must be first. Oh, come on, really? Oh, mouse, actually, oh, tablet pen. So citation, link, discussion. So there's just a couple of the kind of touching points down underneath. Does anybody have any questions about that? if you do, make sure you send me a message, an email. I can answer them now. But just trying to give you guys a heads up so you can go pick an article that you really want to do, rather than waiting to the last minute and have it be a dreary assignment for you. The whole idea is to give you something to research extra on top of what you might not normally do. Make it personal. That's why I can't emphasize that enough. Should be something that, motivates you, you're passionate about, why you get up in the morning, why did you come to Full Sail? All right, so if you choose to use EBSCO, you'll get kind of a landing page like this. You'll be able to get a PDF, you'll be able to get a citation, and you'll be able to get the permalink. One thing you have to avoid with EBSCO, if you choose to copy the URL in your browser and use that as your link, as soon as you quit out of that session, that link is no longer any good. I get it. I will get something like this. And I get many of those every month. So what you need to do is in EBSCO, use the permalink. That will give you a link that is good for anybody, whether they are signed in to Full Sail's network or not. Now, if you are doing Game of Sutra, game developer, or game studies, you can copy the URL from your browser, because you're not going through Full Sail's network to do that. And remember, EBSCO is kind of a national database of universities, libraries, research systems. So it's not just Full Sail. It's, Rollins down the road, and UCF and USF and, U of F and every other Florida university and nationwide. So like I said, if you forget and give me the incorrect, if you're in EBSCO and you just copy it out of the URL in your browser, this is what you'll get. So there's going to be points deducted because I can't get to the article to look at it and verify. And so a lot of times, if I see an article that you guys are doing and I read your comments, I'll go find the real article for myself and read through it, because what I found was interesting from what you said, and I want to see more, because it's going to relate to everybody differently. So a lot of times there are also, for really long articles, and this usually goes for game studies, or in some cases, what are called white papers that are available on EBSCO. They contain a very special format to give you an abstract, which is basically an overview of what the article is about. And then they give you the full article. We need the full article. Some of the links in EBSCO only give you the abstract. That's not going to work. You need to see the whole thing. And if you've done it correctly, you've got the citation, you've got the link, you've got the discussion. I click on it and it takes me right to the article, and I can kind of look at it too. All right, so like I said, if you have any questions, let me know. I'm telling you this now so you guys can get a jump on doing some research for this discussion, because this is all you doing research. All right, any questions before we get going? We're going to talk about materials now. No? How about out there in Zoom? Anybody got questions so far?
I'm all good.
Okay, thank you.
All good.
All right. So let's start to talk about material properties. And this kind of relates to the lecture 2 of why we see what we see, how we see. This time it's not based on us, it's based on what light hits, the objects that reflect light. What gives us the visual clue that something is smooth, that something is rough, that something is wood, concrete, cloth, metal. So this type of reflection is what we encountered in the very first talk about basic materials. So what type of reflection is this sphere exhibiting? Now, don't forget, in addition to this, we've also got a diagram going on here, and this should give away pretty much the entire answer. Okay, AI standard surface. But remember, when you create a default AI standard surface, you get specularity turned on. You get that spec weight. This is without the spec weight. So what is it that we're seeing? This actually has a technical name, this type of reflection. It is matte, but that's technically not the term.
Opaque.
Well, opaque just means that we can't see through it. So yes, it is opaque. So not refraction because it is not transparent. You need transparency for light to be visibly bent as it passes through a surface, which is what refraction is. Say again? Roughness plays a part in it. It's right here. We got microscopic irregularities. We've got organized rays of light that come in and hit the surface. They hit that surface, and then those light rays scatter. I heard somebody in Zoom. What did you say? I missed it.
I said reflective, but I said it too late.
Yeah, reflective is just, I mean, everything is really reflective or we wouldn't see it. It reflects in some way. Okay, this is a diffuse reflection. That is the correct technical name for it. Diffuse reflection. People say, oh, the light rays are being absorbed. Well, technically, no, because if the light rays were being absorbed, all we would see is a black empty hole and have it look like Vanta black. It is reflecting light. Now, the whole other argument is, okay, it's reflecting light, but why is it that we see red? And we see red because red is the color or bandwidth that is reflecting back to us. The other colors are being absorbed. But this is a diffuse reflection. So a diffuse reflection has no environment reflections. Abbreviate that. And has no direct light or spec highlight. That we're used to seeing on materials. All right, so again, this is a fairly rough surface, but it's microscopically rough. Wouldn't be one of those things where you would look at it and go, wow, that's going to feel like sand or like sandpaper or something really, really visibly rough. This is going to be on a microscopic level. So a reflective surface is a smoother surface. So we have light rays come in, light rays bounce back in a more organized fashion. If light rays bounce back in an organized fashion, we get to see environment surroundings in it to some degree, depending on how smooth this surface is. So you can see here over on the right, we've got this angle of incidence coming in. That's the light. And the angle of reflection, that's what bounces off of the surface. So you can see it comes in, hits the surface. It doesn't get distorted. It doesn't get broken up. It doesn't get scattered. It comes back in a more organized fashion. That's why we can see environment reflections. We also get the ability to see direct light highlights. All right, so a direct light highlight is basically light hitting a surface, bouncing off of it, and finding its way into the camera or your eye. So, sorry, Zoom people, got to go up to the board and give a demo of it. But basically what I'm going to try and show them up there is, hopefully you can see the highlight from the overhead light there on my phone, right here. Okay, so I can see that it's pretty clear. It's rectangular, just like it is. And it's got pretty decent detail. You can see all the different lights in the room. Can see some pretty decent environment. And that's because this surface is very smooth. It's like glass. So we've got our direct light coming from the projector. Right? That gives me a nice kind of round circular highlight that everybody should be able to see, hopefully. Right? Coming off the projector. Right? We're seeing that reflection because light is coming from the projector, bouncing off of here directly into your eye somewhere. So that is a smoother surface that gives us environment reflections and also gives us direct light highlights. Now, everything that we measure in CG is based off of the angle of the camera to the subject. The subject is made out of what kind of geometry? Usually. What are you guys modeling? What kind of surfaces do you use? That's not a surface. That's a material. Say again? No, what are you guys modeling? Say you start with a sphere and you start pushing and pulling stuff. What are you modeling? What kind of geometry are you using?
Polygon.
Polygons, yes. Thank you, Julio. Polygons, we do polys. So polygons, as the name implies, are triangles. Now, we use quads because they're a little bit bigger. It's a little bit easier to manage. But in the end, when everything gets rendered or everything goes to a game engine, it gets turned into triangles anyway. Everything. Don't forget that all of our quads have what are called surface normals. You guys should be familiar with normals from modeling. You get a normal that's flipped, what happens to your surface? Stops getting light, what does it look like? Yeah, it looks black. It looks like a black hole, right? Because it's not reflecting light. That normal is telling it to reflect light in that direction. So light comes in, hits the surface, bounces off, and it's recorded by the camera and the renderer. All right, just to kind of drive this home a little bit more, Let me fire up Maya. I'm going to create a simple sphere, put a camera in there, just to kind of show you what we use those surface normals for. Now, in gaming, we also use surface normals for collision. We use it for reflectivity. We use it for lighting. We use it for visual effects. Particles hit things, they bounce off of it. What happens when they bounce off of it is determined by the angle of the normal to the angle of the camera and the code that's in that particle. What is it supposed to be doing? All right. Oh, good. Okay, that worked out pretty good. Front, that works fine. Let's go polygon right here. Let's scale it up a bit. Go perspective also. All right, so here is our famous polysphere. Right? Each one of these quads really is two triangles put together. Now, I'm sure you're all familiar with, in order to make this surface normals display, you go display, polygons, face normals. Right? And you got all those little hairy things that show up. Let me make it smaller. It's a little easier to see because they're bigger. All right, so all of those little normals are playing a very important role when we're talking about reflectivity, when we're talking about collision, when we're talking about transparency, we're talking about any aspect of visibility, because everything is based off the angle of the normal to the angle of the camera and where the light is, where the particle is, and everything else. So again, if these normals are reversed, let's go back here. There we go. Reverse. So now it's a black hole. But if I go inside, you can see all the normals are facing inward, and it looks pretty bright inside. Go outside, all dark. All right, now, typical reflective surfaces are a product of three main components. The first one is the base part of the material, the diffuse. The second is actual reflections. The third is specular highlights. When all three are added together, remember, almost everything is additive that we're doing in CG, we get final surface reflectivity, which is color, diffuse base, actual surface or actual environment details, direct light highlights. This is technically called an isotropic reflection. Standard isotropic reflection is a normal average reflection. So again, going up to the board real quick. So average isotropic reflection. Nice round highlight from the light. Okay, same light source, but on an anisotropic material, notice what happens to the light. It is no longer a nice little round visible highlight. It is now stretched. And that is because this piece of brushed metal has horizontal brush strokes in it. Those horizontal brush strokes make the light stretch vertically. And an anisotropic material, which is what this is, always reflects the light perpendicular to the rock. And brushed metal is unique from a normal, just average rough surface because it's intentionally in a direction. Does that make sense? So no matter how I turn this, that reflection is always going to be perpendicular to the roughness. Turn it sideways, the roughness is vertical. Turn it upright, roughness is horizontal. Notice how that reflection shifts. On a typical isotropic reflection, I can turn it all I want, and all I'm doing is just rotating the object, but the reflection stays the same. Does that make sense? All right, so everybody in Zoom, see if we can make this a little more accessible. So isotropic reflection is basically me being able to turn my phone and you being able to see how the light doesn't really change as I turn it. That highlight stays the same. Now, with an anisotropic reflection, it's got intentional horizontal roughness. So all of the light gets stretched vertically. It always is perpendicular. That highlight stretches perpendicular to the roughness. So I have horizontal roughness, I have a vertical stretch. I turn the object on its side, and now my stretch is horizontal because I have vertical roughness. Anisotropy. This one, isotropic or isotropy. Anisotropic, isotropic. Does that make sense?
I got it.
Okay, Nelson's good.
Good.
Okay, good. All right, now this also takes us to color. Because today our three-part formula will be how reflective is a surface, how rough is the surface, and then what color. Those are the three components we're interested in today. How reflective is it? How rough is it? In the end, what color is it? We don't add color till the end because we want to try to look at the surface without thinking about color, because a lot of times as humans, we are distracted by shiny and color and motion. So we need to try and minimize as many distractions when we're trying to learn about what materials do. Now, went to an Unreal Fest a little while ago. They usually have a virtual festival, which is actually really good, at least once a year. It's usually around March, April. So if anybody, gets a chance, go take some of them because they have all kinds of free seminars you can do. And they're all virtual and free, even the best price ever. So we went to one of them and they were talking about PBR materials. PBR materials are basically the advanced rendering materials for real time. They are equivalent to like the AI standard material or the RenderMan standard material or the V-Ray standard material. They're basically how materials handle reflectivity, transparency, all the different aspects. But this part was all about color. And they said a lot of times they have a lot of problems with new artists working at Epic because they don't understand that things are not pure black or pure white. As an artist, we see something really dark, we go, oh, that's black. And immediately drag the slider or just make it black in the color picker. But that's not correct. In the real world, visually, if you were to take a picture of a black object, it would be not totally black, but really dark gray. just like white objects, would not appear to be pure white. They would appear to be very light gray. So they were given examples of, what they decided to do as a test. So they basically found a really dark photo, charcoal, really dark. Looked really dark, looked almost black. Took it into Photoshop. They used the eyedropper on it, and they found that charcoal is about 0.02 in value. Now, in order for something to be pure black, it would be 0.00 or 0 itself, right? So the thing that makes CG look CG is everything too perfect, and color and value are one of them. Pure white, pure black, stay away from them. So for example, they took somebody went on vacation, they were Colorado mountains or somewhere up in, Northern California. They were skiing, they took pictures, they sampled the images, and they found that the snow wasn't 1, which is pure white, it was actually 0.81, or they said it was ranged between 0.8 and 0.9. But you want to avoid pure whites, pure blacks. Does that make sense? So you see something black, think really dark gray. You only want to reserve pure black for Vanta black or, a cut between scenes where they might put a pure black frame in. But that's pretty rare. What's that? Or an endless void. But even then, if it's just black, you don't get a sense of it being endless. So usually there's going to be some kind of gradient there, to really artistically to emphasize it. But I see what you're saying, yeah. All right, does that make sense? Questions, anybody?
I'm good.
All right, thanks, Nelson. Julio, questions?
Good.
Thank you. Lanika, Shanti, Willie, Gaetano. All right, thank you. All right, so let's go take a look at some ordinary objects. So for this, I have my mouse that I like to use because it is made up of several different types of materials. The reason we have you guys model these things like they exist in the real world is because in manufacturing, they will be put together and they may be put together with different material properties. So for example, I've got this really, really shiny part in the back. Very smooth, very dark plastic, which is what I've got here. Okay, top of the mouse, I've got buttons, and that's a different material property. So the sides are rubber. Very, very hard to see any reflections at all because it is so rough. But it's there. It's just very, very dull. So, like I said, the reason I like this is because this gives you three really good examples of different material properties. So the one on the back, that's dark, smooth plastic. That is going to be a low roughness surface. Now, sometimes in CG, you will hear roughness called glossy. You will hear it called, oh, it's a high glossy material, which is maybe it's very shiny. So this would be high gloss, low roughness, sharp detailed reflections, Like I said, the button on the top, same light. This is at my desk. I've got a fabric hat right behind it so you can see, and it is a dark, well, you would typically say it's black, but it's really dark gray. And you can compare that to the dark plastic. And you can also see that the hat is fabric and it doesn't exhibit any environment reflections and no direct light highlights. So my hat would be a diffuse material. This one would be reflective. This would be isotropic. All right, now, there we go. All right, so same lighting, same rectangular light, same environment, rougher surface. This would be medium to high roughness. The reason I say medium is because it's not nearly as rough as the rubber grip on the side. So this would be a low glossy surface, medium to high roughness. It's going to have blurry looking reflections. That's because the roughness on the surface will tend to break up the light coming off of the surface. It's really soft highlights, soft meaning blurry. Now, that rubber on the side is rougher still. So this would be a very high rough surface. So you can see what happens to that light reflection. The rougher the surface, the more you lose detail. So really dark gray, very rough surface, very low level of glossiness on the surface. Very soft, almost diffuse, but not quite. Remember, the hat's diffuse. You don't see any of that light reflection in the hat. But this still has a little bit of reflectivity, but a lot of roughness. Does that make sense? Now, the thing about working with materials in the very beginning is, you know, we talk about how reflective is the surface, how rough is the surface, what color is it? All right, well, sometimes you want to start with full reflectivity, get the roughness in there, and then if it's too reflective, you dial back the reflectivity a little bit. If that highlight, even though it's broken up or blurry, is too intense compared to the reference. And by the way, you will have reference for everything, because part of your job today is to also find reference for the objects that are in your interior scene and your exterior scene. They are all going to have their own material. It's not like we did for lighting where we assigned one blanket material to the whole thing. Now we're going to be assigning for the exterior. You got a table. It's going to have its own material. You got legs on the table. That's a different material than the tabletop. You've got the beams. They're going to be metal. You've got wooden insets inside the beams. That's going to be different material, different surface. So in the interior, you've got the floor, you've got sofas, you've got pillows, you got walls. You've got little objects in the scene that are all going to have their own material, their own AI standard surface. So you're going to have quite a few AI standard surfaces in there. I recommend, as you're making them, label them so you know what they are. Because if you go, oh, AI standard 74, you're not going to remember what that is from 35 or 11 or 5. Label them. That way you won't drive yourself insane. Now, we'll talk about reference, or we'll talk about reference when we get back from short break. I'll kind of go over that. But when you're looking for reference, part of the thing is going to be, if it's visible to the camera, it needs to have its own material and its own material properties. So if it's visible in the long shot and the close-up, it needs to be unique in its own material. All right, now, until today, we have been using 100% of the material's energy in the diffuse. Today, we are stealing energy from the diffuse and adding it into the reflection or the spec. We'll deal with refraction or transmission on Wednesday. So as we steal from the diffuse, it was at 100%. Now it's going to come down and the specular is going to come up. Why? Because you can only have 100% of energy at any one time in any one location to make something physically accurate, which is what we're after. We're after physically accurate materials. When we add more reflectivity, the energy stolen from that diffuse. Now, some parts of the material are automatic. Like when we start to add in more specular or more reflectivity, it will automatically be stolen from the diffuse. Other parts, like when we start dealing with transmission in glass, we're going to have to manually kill we're going to have to kill that diffuse. Because typically glass is not diffuse. Glass is mostly transparent and has a good deal of reflectivity, but that's pretty much it, even if it has color in it. All right, so in our Arnold section, right under base, we have specular. And we've got two different ways to make materials. So as I mentioned, we have things called dielectric materials, and we have things called conductor materials. Easiest way to remember it is, if it's not metal, it's dielectric. If it's not metal, it's dielectric. So you say to yourself, what is that made of? My mouse. My mouse is all dielectric. There's no metal in here. It's all plastic, rubber. And that's pretty much it. Plastic and rubber. Most of our objects are plastic, rubber, fabric. Yes. Would what? Water, yes, it would, because we're going to calculate water just like we would glass. Because water is mostly transparent, unless, of course, it's dirty, which don't drink. And then it's reflective. Very little, if any, diffuse in it. So the thing about conductor materials are, they are all going to be metal, because metal behaves a lot differently than the other material properties. So for example, when you look at a piece of metal, you'll notice that when you look at it, most of the color comes from you looking at it directly, and the edges are not as reflective as a normal material. Usually metal has dark edges, whereas a normal average material will have light edges and a, less reflective in center. So if it's not metal, it's dielectric. So for dielectric materials, we've got the base color that's going to be, what is it? So for example, my mouse, the back here, that base is going to be really, really dark gray. The top is going to be lighter gray. The side is rubbery, but it's going to be dark gray also. Pretty dark gray. Specular weight, specular color. Here's the deal with specular color, and this confuses people. Specular color is only changed for metal. We don't change specular color ever for anything other than metal, and only for what we call red metals. The reason is all the color you see in a material comes from the base or comes from the environment reflecting in the base. So for example, take a look at my mouse here. You can see I got a little bit of blue, a little bit of red, a little bit of white. Okay, that's all reflected environment. Now, conductor, we have a control under base called metalness. Once you turn that all the way up, the material automatically becomes reflective like metal. And then all we're doing at this point is changing the base color, the specular weight if needed, and if it's red metal, we change the specular color to be red also. Now, here's the deal with metals. Metals are broken up into two categories. There's white metals and there's red metals. So steel, which one would you think that would be? Yep, I would agree with that. How about copper? Copper is going to be red. Even though it's orangey, it might be yellowy, it might be, you know, somewhere in between. It's still considered a red metal because those are the primary rays that are being reflected off of it. How about aluminum? White. Anything that you might consider to be silver or gray, that's white metal. That's because it reflects all bandwidths of light equally. Remember in our very first discussion on lighting, we had a red light, blue light, green light. When they all overlapped, we got white. That's what's happening with white metal. So steel, aluminum, iron, what would you call that? Yeah, call it white. I mean, it's really dark gray, but yeah, you call it white. How about gold? Yeah, gold would be considered to be a red, even though it's kind of orangey, goldish color. Silver, yes. White gold. White gold would probably be white, depending on how much, whatever it is they add to make it white, which I think isn't a combination of silver. Yeah, it depends on what the property is. It might be, actually, it might be somewhere in between. Like white gold, I'm not really sure is white. I think it's kind of really light pink. Okay, so yeah, it would be good to find out what the alloy is. All right, brass. Yep, that's going to be red. How about bronze? Yep, that's going to be red also. So remember, if you're ever not sure, just look at it and say to yourself, does it have color in the metal? Is it bronze? Is it brassy? Is it gold? Is it copper? They'll tell you right away that's red metal. All the other metals, titanium, chromium, stainless steel, they're all white metals. Nickel, you name it, it's probably white. All right, so we got red, we got red, we got red, we got red. Over here, we got white, we got white, we got white. There are metals that are designed to change color or to kind of give you that rainbow effect when you look at it at different angles. And that's usually because it's got a coating on it. Like if you take metal and then rub like oil on it, you probably would get that rainbow effect depending on how thick the oil is, what kind of oil it is, and how you held it up in the light. It's kind of similar if you ever see an oil stain or like fresh oil on asphalt or concrete. You can kind of see that rainbow effect from it. So yeah, if it's coated, it could definitely do that. Like car paint, the way that they have cars where it can look turquoise in one direction and maroon in another, that's basically the flecks of paint being multicolored. And it's put on, takes a lot of work to do, and it's an expensive coat to make sure all the red goes in the right direction, all the blue goes in the other direction. Does it make sense? Yep. All right, so dielectric materials, as we started to say, the base color, this is how we view that object when we look at it directly. You will see a lot of reference to 0 degree and 90 degree. All right, so 0 degree, face camera directly. 90 degree, sometimes called a grazing angle or a glancing angle. We're basically looking at the edge of an object. Specular weight, that's the brightness of the specular highlight. And the color should be white, again, should be white for all materials except red metals. One of the common mistakes is for people to start throwing color into the spec, because that changes your reflections unless it's metal. All right, dielectric, or I'm sorry, conductor materials. This is metal, right? Under base, you turn metalness all the way up, it's going to shut down the index of refraction under specular and also the diffuse roughness under base. So the base color, that is, what is the metal when you look at it directly, facing you, the camera, however you want to interpret it, right? It should be gray or white for all metals except red metals. Specular weight, this, for specular and metal, this involves the edge of the metal. So as soon as you turn up metalness, the base is you looking directly at the material, and specular is the edge of the object. Specular color, again, white, unless it is a red metal. We're going to go over this many times when we start making stuff. So just try and take it all in, take notes for yourself, whatever kind of makes sense. Now, the one thing that conductor materials and dielectric materials all have in common is roughness. Roughness is found under the specular section. This determines how the reflections look. Are the reflections very smooth, very detailed, high glossy? That's low roughness. As we increase the roughness, the reflections become blurrier. They start to get spread out. The default that you get from the AI standard material for roughness is 0.2, which is actually considered to be moderate roughness. And you would think, oh, well, wouldn't like 0.5 be moderate? Well, no, just because it goes from 0 to 1 doesn't necessarily mean 0.5 is moderate. 0.5 is actually very rough, as you guys will see when we start playing around with this. That's why we say kind of the magic formula is how reflective is an object, how rough is an object. Then once you've determined those, what color is it? Now, we kind of went over anisotropic a little bit with my water bottle here. This is brushed metal. Brushed metal is actually very easy to create in Arnold. It's under the specular section. There are two controls. One is called anisotropy, and the other's called rotation. Basically, all it is anisotropy is turning from 0 an isotropic material, like the front of my phone screen, to anisotropic when you get close to 1. Now, a lot of times I will not take my anisotropic all the way up to 1, because sometimes with the Arnold denoiser, it kind of looks funky if anisotropy is too high. But somewhere between 0.9, 0.95 will give you a really good anisotropic reflection. Now, the only thing you have to do after that is to rotate that highlight, because Arnold doesn't know where the roughness is going to be. You have to tell it where it's going to be. So you would think rotation, great. Isn't it 0 to 360? No. To make it harder on you, it's 0 to 1. And you say, what? That's stupid. I agree. Completely stupid. But rotation, if you think about it this way, if I want to rotate something 180 degrees, which would be doing that, I would rotate it 180 degrees. But if I only have 0 to 1, I would go 0.5. Right? Because if my rotation is limited to 0 to 1, 1 is 360 degrees. So 0, 1, they're the same. 0, 360 are the same. So if you want to rotate something 180 degrees, that'd be 0.5. The most common rotation for an anisotropic material is 90 degrees or 0.25. Because if you break up a rotation into 4, every 90 degrees is a quarter of 360. Remember, 360, you cut it in half is 180. Cut that in half, it's 90. And those are the most common, rotation numbers. Is basically going to be 0.25. 0 is going to be a wide stretch for an anisotropic highlight, and 0.25 is going to be a vertical stretch. Very similar to the way this bottle works. So to kind of drive that home, took off the laptop there, took a couple of renders of this brushed metal thermal bottle that we have in there. All right, so the one in the center, this is 0 anisotropy, 0 rotation. You can see it looks pretty rough, not much in the way of detailed reflections. On the right, the anisotropy was increased to 0.95, and you can see it stretched so much horizontally that it almost gets rid of some of that roughness. Same level of roughness, 0 rotation. On the left, 0.95 for anisotropy, 0.25 for rotation. Now I get the nice stretched highlights like I have on my bottle here. And most thermal containers like this that are brushed metal are going to have horizontal brush strokes. Aesthetically, it's a lot more pleasing than having vertical brush strokes and having a wide stretched highlight. It just seems to flow with the form of the shape. So basically, you set your material up to be metalness. You put in the appropriate base color and the appropriate specular color, which is usually 1. If it's a white metal, the edge color is usually 1.0. It's usually full-blown white because most objects are super reflective on the edges. Now, a couple of tools for today. We've got the, let's get rid of that. We've got the refractive index database, which will help us get some numbers for our objects. That'll help us get the reflective values for the different kinds of metal. And also the Arnold Maya user guide. This will talk all about the AI standard surface. It's really a good resource because they go into detail. They will render out using those little shader balls what the different attributes inside the AI standard surface do, what they look like, how they work. I've also got a link in there for why copper is reddish in color. It's a scientific PDF, 2 pages. The first page is easy, humans can read it. The second page, get a calculator. If you love math, the second page is for you. For me, I was chased down a dark alley by math as a kid and frightened. So I love math, but I'm not that good at it, to be honest. But all this stuff is really interesting to read. Now, as we start playing around with reflectivity, guess what that's going to do to our render times? They're going to start to go up because now we're not just worried about camera AA samples and diffuse samples. Remember, diffuse is indirect. Now we're worried about what reflectivity on a surface looks like. So your camera AA and your diffuse may have looked really good for project 5, but now we're adding in reflective materials, and now you may see some noise in the reflectivity. If you do, you need to increase the specular in your sampling section under the render settings. Now, just be careful because this is multiplied by the camera AA again. So think of medium is going to be 4, medium high is going to be 6, high quality is going to be 8, but with high quality, if you really need that many samples, expect it to take at least 2 or 3 times longer to render. All right, does that make sense? Just a little word of, just a little bit of advice. While you're busy playing around with the material, you don't have to worry about increasing them that much. But if you're trying to figure out how to make something look really good for a final render, then you're going to have to start factoring in that specular also. All right. Any questions before we go on break? It's a good time to take a break. We come back, download the Lecture 6 demo files. We'll be able to, basically, I've got a very simple scene. Helix, a plane, a sphere. We're going to be assigning some materials. We're going to be trying to get different levels of reflectivity in plastic. We're going to do some metal. And we're also going to talk about what to expect when you guys start looking for reference, because we've got some guides for you here. Like I said, in addition to the reading, we've also got the SAL Look Development Guide for materials and textures. So I highly advise you to download this. This will tell you what kind of reference we're looking for, what's appropriate reference, what's not appropriate reference. Today in lab, your lab instructor, Frank, is going to give you a pretty good, thorough demonstration and discussion about look development reference. All right, any questions in Zoom before we go on break?
No, sir.
No question.
Okay. No questions. Thank you. How about class? Any questions? All right, so let's see. Come back at 2:52. Give me a couple of minutes to make sure, since we're having Wi-Fi issues, to make sure lecture's uploaded and everything's rendered out. All right, so I'll see you guys back here in about 20 minutes.